Thank you, the organizers, for inviting me to give this talk in this amazing workshop. And today I'm going to talk about multiferroic van der Waals materials. So I will try to combine some of the things that we have already been talking about, but all together in multiferroic van der Waals. So first of all, well, these are the works I'm going to talk about. Basically, I will talk about what is the first purely 2D multiferroic in the first two works. And then I will talk how, with van der Waals materials, van der Waals magnets, we can engineer artificially multiferroicity by twisting them. And more importantly, well, in these works, there was people more than me involved. So yeah, basically, and also from different universities, you have all them here. So yeah, I was saying that there was people involved here. So you have all the faces of the people involved in these different works from Aalto University, Princeton, Madrid, and Jyväskylä, also in Finland. And yeah, so let's start motivating these van der Waals multiferroics. So we have two keywords. We have, first one is multiferroics. And multiferroics are materials that simultaneously display more than one ferroic order. So for example, we can have simultaneously magnetic order and also an electric order. And when we have more than one order together, we can have a coupling between them. In this case, we might have a magneto-electric coupling. And this offers new opportunities in terms of applications, because we can, for example, try to think of modifying that magnetic order by applying external electric fields. So that's why these kind of materials will be promising for those kind of applications. On the other side, the other keyword that we have is van der Waals materials. They are made of different layers, we know. So they have a weak van der Waals coupling. So thanks to that, for example, the well-known case of graphite, we can reach easily the 2D limit of these materials. And as we know, graphene is not the only 2D material. We have many more. We have already talked in this conference about one of them in particular. But here I show another ones with different properties. We can have superconductors. We can have ferromagnets. So the key point of this is that we have a whole family of 2D building blocks that we can, thanks to this weak van der Waals coupling of the layers, we can easily stack them together and create heterostructures with novel functionalities. And also, this weak van der Waals coupling allows us to twist in an easy way these layers without suffering too much reconstruction. So these are the kind of good points of the van der Waals materials. They are quite flexible for that. So now we can think, OK, do we have already a van der Waals multiferroic? And the answer to this question is that yes, we have this one, which is called nickel iron 2. Like a couple of years ago, it was shown that well, this material already in bulk displays a multiferroic order, a spin spiral multiferroic order. But it was possible to isolate it at the monolayer level. And by terms of using optical techniques, it was possible to determine that there was some sort of evidence that the multiferroicity was still there at the monolayer level. However, these kind of optical techniques do not allow to characterize the multiferroicity, the order parameters of the multiferroic. And also, if we think about the typical techniques that are used in bulk, like, for example, neutron scattering or other kind of measurements to determine the polarization, neutron scattering, for example, to determine the spin spiral order, the magnetic one, these are not possible to be used in the monolayer level. OK, they are challenging. So what I'm going to show is, first, what is the origin of this multiferroicity in this compound? And then we are going to show that is it possible to have a new method to characterize this 2D multiferroicity? And in particular, it's going to be with using a scanning tunneling microscopy. OK? So let's start. This is nickel iron 2, nickel in gray. This is the structural unit cell. So yeah, this is the structural unit cell. Nickel gray, iron 2. This is a top view of it. So the thing is that nickel is in 2+ state, so it's a spin 1 state. So we have a magnetic atom. It's insulator, so we can describe it using a Heisenberg model, a spin Heisenberg model. And in particular, the important terms here for this compound are the first neighbor magnetic exchange and the third neighbor magnetic exchange that I highlight here with different colors. And the point is that they are, the first neighbor is ferromagnetic, while the third neighbor is anti-ferromagnetic. So when this happens, a competition is established between them. And the kind of magnetic order that we end up having is this sort of spin spiral order, which is described by this Q propagation vector, also the rotation vector of the spiral. But you can see here that now we need a much bigger supercell to describe this spin spiral order, right? And the periodicity of this is given by the Q, which is determined by the ratio between these two parameters, the J1 and J3. This is what determines how is the periodicity of our spiral. So at the end, what we have in space is a modulated magnetization with, for example, this kind of sinusoidal phase, which is changing direction locally in the space with the spin spiral. Importantly, it has been shown already many years ago that for this kind of spin spiral magnets, when there is a strong spin-orbit coupling present in the system, this is given by this equation here. The spin-orbit coupling will be this lambda parameter. So you see that when we have this sort of non-collinear order, this will be non-zero, this curve. And this will give rise to an emerging polarization in the system. So for this spin spiral, if there is a strong spin-orbit coupling, we will have that emerging polarization. And we show here in this work that this strong spin-orbit coupling is due to the iron atoms of our system that provide that strong spin-orbit coupling. So the picture now is that apart from this magnetization, we will have also an associated polarization that you can see here using that equation that will also present a modulated behavior. But in this time, the periodicity, in this case, for the polarization is half of the spin spiral. OK, so traditionally, the way to think about this was this paper. In terms of measuring an electric polarization in a macroscopic scale, one will take, for this equation, the average, and only the component which is perpendicular to the propagation vector will remain. So traditionally, this will be some sort of average electric macroscopic polarization. However, we have seen that at the atomic scale, we will have that electric polarization. So we need something that is able to prove that atomic scale, and that is precisely an STM. So we can go with STM, and if this is the case of having this multiferricity, this electric polarization should induce a modulated electrostatic potential, and with the STM tip, we should be able to see that. Okay? So we went to the lab. Just recall that we don't need any sort of spin polarized technique, just the STM, just to this magnetoelectric coupling. Okay, both things are coupled. So no need to spin polarize the STM, just. So we went to the lab, we ultra high vacuum, we synthesize a monolayer of nickel iodine 2 on top of HOPG. This is a STM scan, large area one. You can see here the island. So we can take, for example, in this point, the blue one, a spectra with the STM. We can also use that to take a spectra. And you can see here that it shows a wide band gap, like of 2 electron volts. But we can take an even smaller scan with more definition. And you can see here that what I was telling you about these modulated stripes are appearing also here. You can see here that we can distinguish 2 multiferroic domains in this scan. Okay? So this is directly a proof that this is a multiferroic in the way that we were saying. We can go further and do more atomic scale resolution to directly determine what is the Q of the spin spiral. So for this, you can see that this is much higher resolution. We have in one of the domains. We can distinguish the atomic positions. So now we can directly map what is the relation between the atomic positions and the periodicity of the spin spiral. At the same time, we did DFT calculations, non-collinear ones, to determine what was the response of the system, so to basically match the experiment with the theory. You can see here that for a commensurate sail, that's what we can do in DFT. That's the one that better matches the experiment. We can see that both things, the stripes also appear. And also, if we fast Fourier these images, we can see here, perhaps here is not that well contrast, but you can see here that there are different peaks. The important part is that this ones highlighted with the red circles are the ones related to the lattice, the atomic positions. And then we will have here these ones, which are the green peaks. We also have them here in the theory. And from then, those are related with this stripe modulation. So from the relation from these all peaks, we can extract what will be the Q of the spin spiral. And this will be typically done if it were a Boole compound with neutron scattering. Okay? So we are directly measuring this with an STM. And also determine the J3, J1 ratio that I was telling you that determines this Q. So we have characterized the magnetic order. We can go further and say, OK, can we also characterize the size of this electric polarization? So the typical way to do that with an STM, if we have a ferroelectric island, will be that we will have a homogeneous polarization in that ferroelectric island. It can be tin telluride, for example. And what will happen is that in the domain boundaries or in the, let's say, edge of the islands, we will have a reconstruction of that polarization, and that will cause a band bending in the conduction band. However, here what we are going to have is that the polarization already is modulated in space. So that is already going to cause a modulation in our conduction band. So basically, we can take, again, a spectra, but now through a line. And we can see here that there is a modulation of the conduction band. And that is telling us a signature of the magnitude that we have of that electric polarization. So we can, again, do the same calculations with the theory. Also, these are the conduction bands. Well, one thing from the FT is that the band gap is quite underestimated, as we know from the FT. But that modulation appears no matter that. So we can see here, if we take now, pay attention to the red and blue spectra from maximum and minimum, we can see here that there is a shift on what will be the maximum of this spectra of the intensity of the conduction band. There is that shift also in the theory. So we can track that shift along that line. And these are the points of those maximums. We can see here that they match quite well to a sinusoidal function. So we can fit to that. And from the amplitude of that cosine function, we can estimate what will be the electric polarization, because that sort of band bending intrinsically there. So that allows us to characterize the ferroelectric order in the system by estimating the polarization. Finally, I want to show you that we can also manipulate domains, these multiferroic domains, with an STM. So this is a scan. The important points here in this scan will be that we have two domains, two multiferroic domains. We have the left, we have the right, and we have a domain boundary in the middle. Then there are defects that I'm not going to talk about, but they can be also analyzed. But let's focus on the domains. So what we can do is take our STM, go to this point here, number 1, and we will go with the tip, and we can create electric pulses there. So we will see how this will reconstruct. And by doing that, we see that the domain boundary moves to the right. So we have scanned the same area, and now the domain boundary has moved. So let's repeat the process. Go now to number 2, do the same electric pulses with our STM. Let's see if this moves again. Now we have sent this to the left. And we can even do a third time the process with the STM tip close to the domain boundary, pulses, and we move again the domain. So you can see that with the STM, we can also control these domain boundaries. Okay? So just to sum up this first part, that was about the 2D multiferroic, the first 2D multiferroic. First work, we showed that this multiferroicity appears as a combination of this spin spiral magnetic order and the strong spin orbit coupling from the iron atoms. And then we have also seen that with an STM, we can fully characterize, demonstrate, and manipulate even that multiferroic order. Okay? So how much time do I have, by the way?
You still have some time, 8 minutes.
OK, great, because that's the second part. So yeah, we have learned a thing now. We have learned that this multiferroic order, from this analyzing this first 2D multiferroic, we know that the multiferroicity here is due to this non-collinear magnetism, this spin spiral. But it could be any other non-collinear. Well, not any other, but some non-collinear could be. Plus strong spin orbit coupling. So those are our ingredients. And now we have van der Waals materials that allow these new degrees of freedom that we can twist, stack them together. So the idea is trying to answer the question, can we artificially generate those ingredients and have an artificial multiferroic. And I will show you now that it is possible to do this by twisting chromium trihalides, which are 2D magnets, and by stacking them and twisting, creating a moire, is it possible to generate artificially a multiferroid? And this is going to be a theoretical work. Okay? So let's pick 2 of these layers, twist. We need to twist them an angle less than 3 degrees is when this is going to happen. There is no magic angles, but you need enough regions, enough small angles. So we have regions that I have highlighted here. So we have 2 kinds of regions in this moire pattern. We have monoclinic regions and rhomboidal regions based on their symmetry. Okay, so the key point of how this is going to allow us to get these multiferroic ingredients that we need is because for the rhomboidal regions, the interlayer exchange, magnetic exchange, is going to be ferromagnetic. So if we have a rhomboidal stacking, that will like to be aligned ferromagnetic, the 2 layers. While if we are in the monoclinic, the magnetism would like to be antiferromagnetic. So you see here that the moire is creating some sort of frustration in the same way that we have before with the J1, J3, first, third neighbor exchanges. But now here is created by the moire. So we are going to use this to generate this non-collinear magnetic order that we need to get the multiferricity. So yeah, basically this is the map of what will be the interlayer exchange. So we have regions that would like to align antiferro between them, and regions that would like in blue to align ferro between them. Okay? Let's take a picture there. Okay, so let's describe this with a spin Hamiltonian. So for a single layer, we will have basically these terms. We have that chromium trihalides are described, well, with this honeycomb lattice. We will have a spin 3/2, so this is quite high spin. So we can describe it in some sort of classical way, this magnetism here. So we will have, they are 2D magnets, so we will have, in this case, the important exchange for these compounds is the first neighbor one, which is ferromagnetic. And then we will have anisotropic exchanges. Okay, so we will have an anisotropic magnetic exchange and on-site single ion anisotropy. This one is not going to be that relevant. It's going to be more dominated by this first anisotropy here, so I will not talk too much into detail about that. So that was one of the layers. Now we want to stack another layer, and we will have this stacking-dependent exchange that you have here, and the way that we have generated that is by doing an interpolation between antiferromagnetic and ferromagnetic regions using harmonic functions. Okay, so this is our stacking dependent. Depending on the position of this moire unit cell, we will have one interlayer exchange or the other. So okay, great. Let's solve this spin Hamiltonian. I told you that we can do it in a classical way. So let's obtain the ground state. And we obtain this sort of magnetic textures. So this, again, is not a collinear magnet. It's a non-collinear magnet. So we have a spin texture. And when this happened, we know this equation was equivalent to the previous one that I showed with the magnetization. But now here is for pairs of spins. This will be a microscopic version of it. So we will have an emerging local electric polarization associated to this spin texture. So this will be the top layer, and this is the bottom layer. Okay? They have this spin texture here. Associated to that, using this equation, we will have this electric polarization. So in this system, we will have this sort of spin texture and electric polarization. Here I plot this set, which are the out and in plane components. Okay. So okay, question that we want to answer: which is the best halide that we can use to get this multiferroic order? So basically, this is going to be determined by the parameters in our model, which are the spin-orbit coupling, which was here, and also the anisotropy, which is going to be giving or touching up what will be the magnetic texture that we have in the system. Okay, so these are the 2 parameters that we are going to analyze, and we are going to try to analyze them in an independent way. So let's start with the anisotropy. Here is a plot of what will be the average polarization of that texture that I was plotting you. as a function of the anisotropy. So you can see here that we have a strong reduction as a function of the anisotropy. This, you can think, makes sense. So having an anisotropy, what does to the system, magnetic anisotropy, is tries to align all the spins in the same direction. So this is bad for having an emerging polarization because everything wants to be collinear. So yeah, we need non-collinearity in the system. So anisotropy is our enemy for this. So this will decrease the multiferroic in the system. So for each of the compounds that we can analyze separately, yeah, the case of iodine will be on the verge of being multiferroic. This is due to the strong spin-orbit coupling that has in the system, because the iodine, again, generates a huge anisotropy, magnetic anisotropy in the system. Okay, so this is detrimental to the multiferroic order. Let's analyze now what happens then with the prefactor, which is also, again, related to the spin-orbit coupling. So everything is related to the spin-orbit coupling. So the way to analyze this is with ab initio calculations. We can estimate it. So for a same spin magnetization, spin spiral, that will be this. We can compute this in a supercell where we will impose this spin texture, which is similar to some of them that we are finding in the Moiré. So we will have this configuration. Again, these two equations I was telling you that you can jump from one to the other. It's demonstrated that they can be equivalent. So this spin texture can be also described with a Q of a spin spiral and with this rotation vector. So associated to this particular spiral, we will have this emergent polarization in that direction. Also, if we now consider a second configuration, which is equivalent to this one, but the only difference is that the Q changes direction, the only thing that is going to happen is that the polarization now goes to the other side. Okay? So having with DFT computed these configurations and including a spin-orbit coupling in the calculations, that's key important point, we can estimate what will be the size of this spin-orbit coupling and the ferroelectric polarization that emerges. This, if you do DFT calculations and are used to estimate, for example, the exchange, magnetic exchanges, this is similar to when we want to estimate the ferromagnetic exchange. You can have a supercell where you generate different magnetic configurations, and the difference in energy between those, you can get the magnetic exchanges. So this is a different trick, but to estimate this other term, but also from different configurations. Okay? So taking the difference from this, and in particular, we are going to take the difference between the forces, we can factor out, and there is going to appear a ferroelectric force. So when this polarization appears, also a ferroelectric force appears that will teeny tiny move those atoms. So by doing DFT calculations, you can get that indeed in the non-collinear texture, you will have the appearance of these forces that are associated to the emergence of that polarization. And you can see here for each of the compounds, the chlorine, bromine, iodine, when going to iodine, the ferroelectric force is much bigger. Here we are using the same spin spiral, so we are factoring out the effect of the anisotropy. So for the same spin spiral, iodine will be the best case because it provides the strongest spin-orbit coupling. Okay. However, I told you that the spin-orbit coupling plays a double role. So it's bad because it provides a lot of anisotropy, but we also need certain spin-orbit coupling to have an emerging polarization. So based on that, we did our estimations that the case in between, the bromine, will be better to have this sort of artificial multiferroicity. Okay? So finally, I would just like to show you that we can also try to analyze the magnetoelectric coupling in this system. So we have a system that has at the same time spin and polarization. We have these textures. So we can now include an external electric field that is going to couple to this polarization P. Okay? So let's include this term in our Hamiltonian. We had before this kind of solutions. Now this electric field is going to couple to the polarization, which is at the same time coupled to the spin through that equation. So if we now increase out of plane the electric field, we can modify the magnetic textures. And we can even get this sort of Skyrmion magnetic lattices with the external electric field in our system. So here I plot another figure where we have the electric field in the z direction. And here is the polarization. We can see this will be the ground state without electric field. We can jump to having this magnetic Skyrmion. And we can even jump more and generate this couple more of skirmions. So we will have lattices of skirmions. And we estimate that this can be achieved with relatively low bias voltages, 1, 10 bias voltage, based on the parameters that we have in the model. So just to sum up, in this last work, we showed that chromium tribromine, twisted, can artificially generate multiferricity. And we have also I have also shown you at the very end that we can also access this sort of skirmion phases, magnetic skirmion phases with electric fields, thanks to this multiferricity that we have implicitly in the system. So yeah, just to sum up, as a final message, I think that I try to convince you that these multiferroic van der Waals are a promising platform to engineer novel technological applications. Thank you.